Okay, heating curve for water. So we looked at this portion when we talked about vaporization. We looked at this portion just a minute ago. Here we're putting the whole thing together. So this is starting at negative 25 degrees where water would be ice, a solid, and we're adding energy and heating it up, melting and then boiling, etc., until we get to steam at a temperature of 125 degrees Celsius. We can calculate the amount of energy needed to do each of these portions of this heating curve. So the heating curve isn't really a curve, is it? It's a series of line segments. Each line segment requires its own calculation. So we've done things with temperature changes before. Let's see, I didn't want that color. So like this part here, where we have water going from 0 degrees, liquid water going from 0 degrees to 100 degrees Celsius. Do you remember the equation we used? Q equals MC delta T. Yeah, so that one's coming back. It never actually went away. Q equals MC delta T. That's the equation you're going to use for any of these sloped line segments where the temperature is changing. The energy needed here depends on how much the temperature is changing. It depends on how much substance you have, the mass of the substance, and it depends on the specific heat capacity of that substance. So you use that equation for heating up the water. You also use that for heating up the ice and for heating up the steam. Now, specific heat capacity for steam, liquid water, and ice are different, and so you have to use the correct one. Here, what's the process that's going on? At 100 degrees Celsius, what's the water doing? It's boiling. So it's going from a liquid to a gas, and what's the fancy word we use for that? Vaporization. So this is vaporization. And so to calculate the amount of heat needed there, we're going to use the heat of vaporization. We don't really have an equation here because the heat of vaporization just tells us how many kilojoules per mole of stuff. So we just use it as a conversion factor, and we can figure out, okay, how much energy would be needed to vaporize this amount of water. In this illustration, we actually have not just a general x-axis here, but we actually have it drawn to scale, and this is heat added in kilojoules per mole. Down here in line segment 2, what's happening? It's melting. And what's the fancy word for melting? Fusion. So for that one, we need to use the heat of fusion. So we can calculate from negative 25 degrees to plus 125 degrees, because that's what's shown in this graph. We can calculate the amount of energy needed, but we actually need to do 5 calculations. Each little step is not difficult, and we've done the steps before, but now we have to add them together, and sometimes that can be a little confusing. So there most certainly will be a problem on the exam that's going to ask you to do at least part of this. So it may start like here at 25 degrees. I didn't mean to do that. I meant to do this. It may start at 25 degrees and ask you to go to 150 degrees. Or it could say, well, what if you have, steam at 105 degrees and you condense it and just finish freezing it? How much energy would be released? So there's lots of different possibilities there. So let's look at an example. This actually is directly related to the graph we just looked at, but we could make all sorts of variations of this. Calculate the amount of heat needed to take 1 mole of ice at minus 25 degrees Celsius to steam at 125 degrees Celsius. any of these problems, you should draw a heating curve. It can be very ugly. It does not need to be pretty. But I personally, as an experienced chemist, if I was doing this problem and really wanted to get the answer right, I would draw a heating curve, because it's hard to keep all of this stuff in your brain. So what I'm going to do is just down here in the corner, I'm going to draw a little heating curve. And the exact slope of the lines, how long they are, doesn't matter. It's just the idea. It's this kind of slopey stair-step thing. So where are we starting at? We're starting at minus 25. So this is temperature on the y-axis. So down here where I'm starting, that's minus 25. Where am I taking this to? 125. And so I know that that is steam, that's the gas state. So here I have heating the solid, melting the solid, heating the liquid, vaporizing the liquid, heating the gas. So my 125 is up here somewhere. At what temperature does this flat area happen? At 0. Now, if this was a substance other than water, you'd have to look it up. But this is the melting point. What is this temperature? 100. That's the boiling point. You need to identify those. Sometimes you'll have the whole thing here. Sometimes you'll have part of it. And then sometimes, just to mess with you, we'll say, well, what if you had steam at 125 degrees and cooled it down to minus 25, ice, how much heat would be released? I would do it this same way. I would still do it forward. The amount of heat released is the same number, just change the sign. I think that's easier than trying to do it all backwards. So we have 5 segments here. We need 5 calculations. So let's first identify what the temperature changes are. What's delta T for that section? Delta T is final minus initial, right? So 0 minus negative 25 is 25. So that's 25 degrees Celsius. What's the temperature change in this line segment? This line segment's going from 0 to 100. 100 degrees. And this last one? 25. Because it's going from 100 to 125. One of the common mistakes students will make is they'll take the entire range, 125 minus 25, end up with 150 if they do their math right. And then they'll use that for all the things. That's not right. You have to look at each segment separately. So let's just start at the beginning. This first segment, we're changing temperature, so we're going to use Q equals MC delta T. So Q equals MC delta T. Well, what's the mass of water we're dealing with? It's a mole, right? How much does a mole of ice weigh? 18.016 grams. We just convert moles of water to grams of water. So we've got 18.016 grams of water. And then we need the specific heat capacity of ice, the solid. And so that's right here. Times 2.09 joules per gram degrees Celsius. Now, if you have, a little brain fart and you forget what the equation is, the units here are a huge clue. If I want to find joules, maybe I should multiply by something with grams and something with degrees Celsius so the units work out. You can fudge your way through a lot of stuff just making the units work out. And then we need the temperature change, which we figured out was 25 degrees Celsius. So I'm going to do all the math at the end. So that is for this segment right here. The flat place is where we have the ice melting. And so we're going to use the heat of fusion, and we don't need an equation, we just use that as a conversion factor. So we have 1 mole of ice, and we're going to multiply by the heat of fusion, 6.02 kilojoules per mole. The moles cancel out, and that doesn't even require a calculator, 6.02 kilojoules of energy. Okay? This next segment, what do we do there? Q equals mc delta T again. So, sometimes you're like, well, why can't we do Q equals mc delta T for all of them? Well, for this horizontal line segment, what's the change in temperature? 0. So you could try, but you're going to end up with 0, and then you'll realize, oh, wait a minute, maybe that was something else. So the next segment, Q equals mc delta T again. The mass is the same. We're dealing with that same piece of water. But now we have liquid water, so we need the specific heat capacity for liquid water, 4.18 joules per gram degrees Celsius. And we need the temperature change for that particular segment, 100 degrees. So I'll do that math later. Horizontal segment here, vaporization. So we're just going to use the heat of vaporization as a conversion factor. We have 1 mole, and we're going to multiply by 40.7 kilojoules per mole. And so that's going to require 40.7 kilojoules of energy to vaporize the water. And then we're taking that steam and we're heating it up. So we have another change in temperature thing going on here. Q equals mc delta T again. The mass of the steam is the same. It's taking up a much larger space than the liquid did, but it still has the same mass. And the specific heat capacity for steam is 2.01 joules per gram degrees Celsius. And the temperature change there is 25. Okay, now I have to do some math. So for this first one, I'm getting 941.336 joules. These questions often don't give the numbers, well, they mess up the temperatures because they don't give the temperatures with enough significant figures. So I'm going to pretend that those temperatures are exact. The 0 and the 100 actually are exact. The 125 and the minus 25 aren't, but we're going to pretend that they are. So then the number of significant figures would be limited by the heat capacity. So that would be 3 sig figs. And then we've got that mass of water times 4.18 times 100 degrees. And so that's going to give us 7530.66688 joules, again with 3 significant figures. And then the one at the bottom, we get 905.304 joules, again keeping 3 sig figs. Any questions?
First one is 25.
Mm-hmm. Yeah, so the first one, this 25 degrees Should limit this to 2 significant figures. I think the person who wrote the question is being sloppy with their temperatures. And so I'm going to pretend that that's 25.0 because it definitely could be measured. I mean, just our glass thermometers here will go to the nearest tenth. It's a little silly, but yeah.
You add them all together?
Yep, then we have to add them all together. It's important to put the units down because some of these are in joules and some of them are in kilojoules, right? So what I'm going to do is I'm going to convert these joules to kilojoules. And I can kind of do that in my head, but you're probably not going to like that. So I'm just going to kind of scribble on here. Converting joules to kilojoules, we divide by 1,000. And so that's going to move the decimal point 3 places. And so 0.941 kilojoules. 1, 2, 3. 7.50 kilojoules. 530. And here, 1, 2, 3. 0.905 kilojoules. So 0.941336 plus 6.02 plus 7.530688 plus 40.7 plus 0.905304 equals. So I add those all together and I get 56.097328 kilojoules. So now we're adding, so we have to consider the other rule for significant figures. When you're adding, it's the fewest decimal places, right? So this number has 2 decimal places. This one has 1 decimal place. This has 3 and 2 and 3. So this is the one that limits the number of significant figures to 1 decimal place. So this is going to be rounded off here and report this as 56.1 kilojoules. And again, I did the significant figures there, assuming that the temperatures were exact or at least more precise than what was specified. Any questions? Again, if you have to do this in reverse to find how much energy is released, do it forward. It's easier. There's a lot less negative numbers. Do it forward, figure out how much energy would be absorbed, and then just change the sign. It's more straightforward than dealing with negative temperature changes. Any questions?